So here we are. Welcome to the final lesson in this continuing education course. This is my personal favorite section, but I'll keep it basic. So without further ado, I give you electron theory. So the objectives of this lesson are to understand a basic electric circuit, know how to use Ohm's law, that's very important, understand the difference between AC and DC, understand basic series, parallel, and combination circuits, and 5, know the difference between actual and conventional current flow. Let's touch on some electron theory. It is known that all matter is made up of atoms. Atoms are made up of 3 things: electrons, protons, and neutrons. Atoms. That red center is the nucleus. The nucleus is dense and has protons, which are positive charge, and neutrons, which are neutral charge. You see that hazy cloud? That's the electron cloud probability. You see, electrons have a negative charge and orbit the nucleus, although we can't exactly determine where that electron is going to be. We can only calculate with advanced mathematics like binomial or Gaussian distribution or Poisson's theory and the like, its probability of being in a certain location. Thus, the electron cloud probability. Essentially, the darker the aqua color, the more likely that the electron is going to be there. More on electron theory. Electrons are in orbits at different distances from the nucleus. Electrons in the orbit the greatest distance from the nucleus are in something called the valence shell. The outer orbit contains between 1 and 8 electrons. Conductors contain less than 4 in the outer orbit. Insulators contain more than 4 in the outer orbit. And semiconductors, well, they contain exactly 4. Valence shell electrons. Some elements have atoms with valence shell electrons that have a strong magnetic attraction with the positive charges in the nucleus. These electrons will not easily move from atom to atom. These elements are what we call poor conductors of electricity and are called insulators. Insulators include things like glass, paraffin, rubber, porcelain, wood, and even most plastics. So on the opposite side of the strong magnetic attraction, some elements have valence shell electrons that have a weak magnetic attraction with the positive charges in the nucleus and will move easily from atom to atom. We already know these materials are good electrical conductors. These are things like silver, gold, copper, and aluminum are all examples of conductors. Let's take a look at the model of a copper atom. The copper atom has 29 electrons in 4 orbits or shells. The lone electron that you see in the outer shell can easily be knocked out of its orbit by a free electron from, say, a generator or a battery. The electron, once free, will collide with another nearby atom in a chain reaction. Elements with fewer than 4 electrons in their outer shell are good conductors. Almost all metals have fewer than 4 electrons in their outer shell and thus are good conductors. This is going to bring us to electrical current. Current is the flow of electrons in a conductor, and this flow of electrons is actually from negative to positive. Electron versus conventional theory. As briefly mentioned in that last part of the previous clip, in reality, we know that electrons flow from negative to positive, and this is called electron theory. However, most electrical diagrams are based on the idea that electricity flows from positive to negative. This is called conventional theory. Now, this seldom causes problems unless you're working with a DC circuit. I'll let you look at the difference in the two theories of current flow by leaving this diagram up for you about 30 seconds or so. It's good to hear it, read it, and see it to really let something sink in. Pay attention to the directions in the arrows. Quick trick if you only have 2. You can just multiply the 2 and divide it by the sum of the 2. By that same token, if you have 2 R's of equal value, then the total R is exactly half any one of those R's. Resistors connected in parallel have different current flows through them unless they have the same resistance. In other words, the current flow through the resistor depends on the resistance of the resistor, much like voltage did. Here is a graphic showing a parallel circuit with different R's, so you'll have different I's. However, you will always have the same amount of I coming in as you will going out because of the law of energy of conservation. That's another topic for another day. We talked about series parallel circuit. Here's a quick and dirty graphic of one. Notice the first resistor that is in series with the 2 parallel resistors, which makes this a series parallel circuit. These are fun because you can do a quick little current division to find the amperage of either of the 2 resistors or loads. Anytime you see resistors, those are representative of loads. Just don't forget that. This is going to bring us to some branch circuits. The circuit may have many branches, but in each branch, the ungrounded wire and the grounded wire and the grounding wire are all attached to the corresponding wire of the feeder circuit. The feeder circuit and the branch circuits meet in typically a breaker or fuse box or distribution panel. This is going to bring us full circle, pun intended, for this lesson and this course. I can't tell you enough how thankful I am for you choosing our course. Me and my team hope that you learned a great deal and will leave a more knowledgeable, competent, and safety-conscious electrician so that you perform your best and return home safely every day. I'm Thomas Rocha for Texas T Continuing Education. Have a great day, and we hope to see you next year.